Hello, this is Dr. Armand today, bringing you another exciting lecture in General Chemistry 1 laboratories. Today we'll be looking at Lab 3, using characteristic properties to determine unknown substances. So sit back, relax, and enjoy the lecture. For Lab 3, we'll be looking at the characteristic physical properties of different substances to determine an unknown substance. And so again, we'll be using, in this case, just like in the last lab, we'll be looking at both physical and chemical properties and changes. Just to kind of recap on what we talked about in last lecture, chemical changes, or what we commonly refer to as chemical reactions, change to form a new substance. So for example, we use the processes rusting and oxidation, because when something rusts, it's no longer what it was. It's turned into something new. So for example, if we write a little basic chemical equation showing the chemical reaction of rusting, we're not going to balance it, but for example, iron plus oxygen gas gives us Fe2O3, solid. And so this is rusting. You form iron 3 oxide. Well, what your product is not what you started with, so it's a chemical change. And so properties that describe a characteristic where the identity changes of a substance is a chemical property. So for example, ethanol is flammable, sodium is reactive. These are chemical properties. So they change the identity of your initial substance. Now, when we look at physical properties, here we're not changing the actual composition, we're just changing its shape, its appearance, its physical state. And so properties are characteristics that describe the substance, which doesn't change its identity. And we have, for example, lots of physical properties: boiling point, melting point, density, which was what the last lab was over, color, solubility. And so in this lab that you'll be doing for lab 3, you'll be looking at the physical properties of boiling point, melting point, density, and solubility to help you assign the correct substance based on the properties measured. Excuse me. So there are two types of properties, and we'll be looking at the two types of physical properties. These are extensive, which depends on the amount of matter present. For example, volume, mass, length, heat capacity. These are extensive physical properties. They depend on the amount of material present. So the more material you have, the more you have of volume, for example, or the more material you have, the longer the length is of your substance. So those depend on the amount of matter present. Now, intensive physical properties, like we covered in last lecture, doesn't depend on the amount of matter present, such as boiling point. You know, whether you have a gallon of water or a liter of water, they're still going to boil at the same temperature for water. Density, whether you have a gram of nickel or a pound of nickel, is still going to have the same density. The same thing goes for color, solubility as well. These are not affected by the amount of matter present. And so 1 pound of water boils at 100 degrees Celsius. Likewise, 1 ton of water boils at 100 degrees Celsius. There's no change based on the amount of matter used. So if we look at 1 pound of feathers or 1 pound of lead, which one weighs more? Well, in fact, they both weigh the same, because the only difference is it takes more of the feathers to make 1 pound versus the lead. So if you were to weigh these, they would both weigh the same. The reason it takes more feathers versus the lead is because the density of feathers is less, so it takes a greater volume of feathers to equal 1 pound versus the volume of lead needed to equal 1 pound. Because the densities are different, it takes more volume to get the same amount of weight. So therefore, they both weigh the same. It's just that it takes more feathers to, to make 1 pound versus taking the lead to make 1 pound. Now we're going to look at some physical properties more in depth. And before we get to that, in your lab manual, there are two figures. This is figure 2. The other one is figure 3. These are very important to help you identify unknowns. So this is a physical property table of different types of solids. We have silver nitrate, BHT, ascorbic acid, etc. And so as you can see, they all have their densities listed, solubility in water. So just to make a few comments, for example, BHT, calcium carbonate, calcium sulfate, their solubilities are very low, indicating they're very insoluble in water, in 100 milliliters of water. We're going to talk about solubility in a little bit. Whereas things like zinc nitrate, silver nitrate have a very high solubility, so they're extremely soluble in water. And ascorbic acid and cobalt 2 chloride are soluble in water as well. So the way you interpret this column is for 200, you can dissolve up to 245 grams in 100 mils of water for silver nitrate. You can dissolve 40 grams of ascorbic acid in 100 milliliters of water, and it will dissolve. Now, if you go above 40, let's say you try to dissolve 50 grams of ascorbic acid in 100 milliliters of water, it'll start to crash out because now you've exceeded the solubility. If I was to take 300 grams of silver nitrate and try to dissolve it in 100 milliliters of water, it would crash out because you've exceeded the amount of silver nitrate that you can put into 100 milliliters of water. Likewise, melting points, you see that for the ionic compounds such as silver nitrate, calcium carbonate, calcium sulfate, cobalt 2 chloride, and even zinc nitrate, these all have very high melting points for most of them. This is because they're ionic compounds, they have ionic forces. It takes a lot more energy to weaken the solid. Now, BHT and ascorbic acid, these are covalent compounds, so their melting points are not as high as their ionic compound counterparts. Now, for boiling points, it's some solids have boiling points. Some solids don't boil, they just decompose. So if you heat ascorbic acid up hot enough, it'll melt at 190, but it'll decompose before it boils. So this happens to a lot of solids. You see it decomposes before it reaches the boiling point of the substance. So it doesn't have a boiling point, it just decomposes. So if you were to heat calcium sulfate up to above 1450, there's a point at which it will decompose into its elements instead of boil. And so this is the one for solids in your lab manual. There's also a figure 3 for liquids. I strongly recommend you look over that, kind of understand what each physical property means on the table. So what are boiling point, melting points? So first we're going to talk about a boiling point. And a boiling point is when the temperature is reached that the vapor pressure of the liquid becomes equal to the atmospheric pressure, and it causes the liquid to boil, releasing its vapor into the atmosphere. So typically when we talk about water, we say it has 100 degrees Celsius boiling point, and that's referred to as the normal boiling point, which is the temperature at which the vapor pressure of the liquid is equal to 1 atmosphere. So you can change the boiling point of a substance by changing the pressure. Now, changing the pressure, not changing the amount. So if you change the amount, there's no change in the boiling point. But when you change its pressure, you're going to change its boiling point. So for example, if you they used to do this in high school when I was in chemistry class. They would take a bell jar, put a cup of water in it, reduce the pressure in the jar enough, and you'll start seeing the water boil at room temperature. Now, it boils at room temperature. It doesn't mean it's going to cook anything because it has no heat in it. So there's no heat being released when it boils. So you can't cook anything. So if you were to climb up to the top of the mountain where the atmospheric pressure is lower than 1 atmosphere, the boiling point is actually going to drop. And this is because the atmospheric pressure is lower on the higher elevations, so the boiling point lowers. And this is why when you look at some foods, it gives you special instructions for high altitude cooking, because at higher altitudes, the boiling points decrease. Likewise, if you were to go to Mars and try to boil water, it would be very difficult because probably as soon as you open the container, it would vaporize instantly because the pressure is so low in the Martian atmosphere. Now, that explains how boiling point is affected by the pressure. You decrease the pressure, you decrease the pressure, you decrease the boiling point. Now, boiling point is dependent on what are referred to as intermolecular forces. So these are the forces that hold molecules together. So for example, maybe you've heard of DNA. DNA is held by the intermolecular force called hydrogen bonding. And so if you take General Chemistry 2, you'll learn about different types of intermolecular forces and the strength of each one. So hydrogen bonding is a very strong intermolecular force, and this is what holds DNA together. Likewise, water is involved in hydrogen bonding intermolecular forces, which is why it has a relatively high boiling point. Now, when we're referring to boiling points, polar molecules typically have a higher boiling point than similar size nonpolar molecules. And so what do we mean by polar molecules, nonpolar molecules? Well, these are things you're going to touch on when you get to the later chapters if you're taking General Chemistry 1, and you touch on it again in General Chemistry 2. But generally, if you have similar size polar molecule and nonpolar molecule, the polar molecule generally has a higher boiling point than the nonpolar. And the reason is because polar molecules have stronger intermolecular forces than nonpolar. But again, we're comparing similar size polar molecules. Maybe they're, for illustration purposes, they're the size of golf balls. Now, if you try to compare a golf ball to one of those yoga balls, well, then obviously it's not going to follow the same trend. So we're comparing golf balls, not golf ball, to yoga ball. And so some examples of polar molecules, and you'll touch more on this in later chapters if you're taking the lecture. Water is a polar molecule, and alcohols such as methanol and ethanol are polar molecules as well. Now, nonpolar molecules are usually what we refer to as hydrocarbons. These are a very common class of nonpolar molecules, hydrocarbons. So oil, which they extract out of the ground, contains hydrocarbons, which is mostly made up of nonpolar or petroleum, crude petroleum, which has lots of different hydrocarbons, which are usually majority nonpolar. So when you have an oil spill, it's very difficult to clean up because it won't mix in the water. It sits on the top surface of the liquid, of the water in the ocean. So some examples of polar molecules: ethane, methane, propane. These all have only carbon and hydrogen atoms, so the formula of ethane is C2H6. Methane is CH4. And propane is C3H8. So you notice in all of these they only have carbon and hydrogen, which is a good indication that you have a nonpolar molecule. So again, boiling point is dependent on the intermolecular forces. Polar molecules of similar size compared to nonpolar molecules of similar size, Polar molecules have a higher boiling point than nonpolar molecules. And these are some examples of polar and nonpolar molecules. So what I want to show you here, this is what we refer to as a heating curve. And we'll get to melting point in just a little bit. This is referred to as a heating curve. And it shows you as you add more heat, what happens to as you add more heat over time, what happens to the temperature and the different phase changes. So let's say, for example, right here you have ice. If we're doing this for water, here we have water, and here we have steam. So as you heat the ice, the temperature increases to the melting point, and this would be 0 degrees Celsius. So as you add heat to ice, the temperature increases until you reach the melting point. Then it goes from a solid to a liquid. So notice now when you're doing what's called going from one physical state to another, there's no change in the temperature. So when ice is melting from a solid to a liquid, melting is occurring. There's no change in the temperature as you're converting from a solid to a liquid. Now, once all the solid has been converted into liquid, it increases in temperature as you add more heat to the water until you get to the boiling point. So the boiling point for water is 100 degrees Celsius. And so when you're at the physical state change from a liquid, let me undo that, looks like a bad L. From a liquid to a gas, there's no change in the temperature. So when you're changing the physical state of a substance, there's no change in its temperature. So as you're adding heat, the liquid is getting converted into a gas, and then once all the liquid is converted into gas, as you add more heat, the temperature increases again. So the main thing you need to notice here is that when you're at what we call a phase change, when you go from one physical state to another, there's no change in the temperature. The temperature remains constant. It's once you converted all of the substance to the new phase, then the temperature starts increasing. So melting point is what happens when you add enough temperature. As you increase the kinetic energy of the molecules, they start to break free. And as they break free, melting begins. So over time, you have this balance between melting and freezing. So the temperature at which the melting rate and the freezing rate are equal is referred to as the melting point or freezing point, vice versa. So as you add more heat, you're going to push it toward the melting side. If you remove heat, you're going to push it towards the freezing side. And so just like with boiling points, with melting points, we have a what's called a normal melting point. So it's the melting point at 1 atmosphere, which is 0 degrees Celsius for ice, which is also the freezing point of water. So here we have a solid. As we add heat, we have this balance between melting and freezing, which is shown here, this coexistence of both. As you add more heat, then it converts all towards a liquid. If you remove heat, it converts back to a solid. So at the melting points is coexistence until enough heat is added or removed to either go to a liquid or come back to a solid. And that's what we're looking at, this heating curve here. At this heating curve, at the melting point, there's no change in temperature as you go from a solid to a liquid. And if you're interested in knowing why, when you take General Chemistry 2, you'll learn about why there's no change in temperature when you go from a solid to a liquid, aka the melting point, or from a liquid to a gas, aka the boiling point. And so melting point is dependent, not necessarily on some degree, the melting point is dependent on the intermolecular forces. However, to a bigger degree, it's dependent on what's referred to as the packing of the solid. So how does the solid pack? So these molecules, when they're frozen, how do they pack with one another? And so you see for ice, which has a melting point of 0 degrees Celsius, packs like this. So these water molecules are forming what are called hydrogen bonds between the hydrogen of one and the oxygen of the other, and they pack in this fashion. Now if we look at benzene, benzene here packs in this fashion, which has a melting point of 5.5 degrees Celsius. Now, water and benzene are kind of relatively similar size molecules, but water is polar, benzene is nonpolar. So obviously intermolecular forces don't necessarily give a good indication of which one would have the higher melting point. It has to deal with the packing of the solid that helps determine which solid would have the higher melting point. So packing of the solid is what determines or packing of the solid affects the melting point. So the more tightly it packs, the more squeezed in those molecules are, the more energy it takes to release them. So based on the packing, that's why benzene has a slightly higher melting point than ice. Now, if you look at the boiling points, well, obviously water has a greater boiling point because boiling points are affected by the intermolecular forces, and water has stronger intermolecular forces, so it has a higher boiling point. But for melting points, what affects them is the packing of the solid. And this should be 100 degrees Celsius, not 1,000 degrees Celsius. And so the next physical property we're going to look at is what's called solubility. So solubility contains two things. It contains a solute that is dissolved in a solvent. And so generally the solvent is the most abundant component. And for most ionic compounds, the solvent is water. Now the solubility is a way to quantify how much of a solute will go into solution. So solubility is the solute of the solute is the maximum amount that dissolves in a fixed quantity of solvent at a given temperature. So as we'll see in a little bit, temperature affects solubility. So again, solubility is the maximum amount of solute that dissolves in a given amount of solvent. And what determines if something is soluble or not is when the solute and the solvent have similar types of intermolecular forces. So if the solute is polar, the solvent is polar, they'll mix. Or if the solute is ionic, the solvent is polar, it'll mix. But if the solute is nonpolar and the solvent is polar, there's no mixing. But now if the solute is nonpolar, the solvent is nonpolar, it'll mix. So that's what we mean by saying like dissolves like. They have to have similar intermolecular forces. What that means is, are they both polar or both nonpolar? Or is it ionic and polar, which match, or polar and polar? The best example of this is if you ever buy like I think it's like a vinaigrette salad dressing. When you shake it, eventually you'll see it separate into a water and oil layer. That's because water and oil have different intermolecular forces. Water is polar, Oil is nonpolar, so they don't mix, and that's why they separate those two layers into those two layers. Now, water as a solvent. So again, the solute is going to be the lesser in the amount. So solvents in the greater amount. And so what happens is when you put the solute in the solvent helps disperse the molecules and breaks apart the solid into individual molecules. And when we use water in particular, it's such an active solvent that it strongly interacts with these molecules, and in some cases could even react with them, as you'll learn in Gen Chem 1. So for example, if you try to place sodium in water, sodium will react with water. So water is a very active solvent. It plays a major role with interacting with substances to help break them apart into solution. Breaking apart means we break apart the molecules that make up the solid to cause it to dissolve. So now this is important. There are different types of solutions based on the amount of solute in solution. So pay particular attention here because this is very important. So a saturated solution contains the maximum amount of dissolved solute at a given temperature. And this is what we call the solubility. So when you read the solubility, like we did for that physical property table a few slides back, that's the amount of solute, the maximum amount of solute that can dissolve in 100 milliliters of water. So if you were to put, I think it was 40 grams of ascorbic acid in 100 milliliters of water, that would form a saturated solution. So example, 40 grams of ascorbic acid in 100 milliliters of water forms a saturated solution. Now, if we were to put less than 40 grams of ascorbic acid in 100 milliliters of water, that would be what we refer to as undissolved solute, but what we commonly refer to as an unsaturated solution. So when you put less than the maximum amount, it's going to be an unsaturated solution. When you put just the right amount, it's a saturated solution. So saturated solution, the amount of undissolved and dissolved is in balance. So that's the maximum amount of solid you can put in, for example, 100 milliliters of water. If you put less than that, it's unsaturated. Now, if you put more than that 40 grams, let me clear up a few things here. So less than 40 grams, it's unsaturated. More than 40 grams, it's going to be called supersaturated. So a supersaturated solution contains more solute than it can hold. And so what happens is it becomes unstable, and just by any type of disturbance can cause it to crash out or crystallize immediately. So over here on the right, what we have is a saturated solution of sodium acetate. They drop a seed crystal in it. Excuse me. What we have here is a saturated solution of sodium acetate. So this is saturated solution right here, saturated. We then add a tiny seed crystal of sodium acetate into the flask, and you can see right at the moment it starts to crash out or crystallize out, because now you formed a supersaturated solution. I think I got that right. So when we add the seed crystal, it forms a supersaturated solution. It then crashes out, and we get these crystals of sodium acetate. Now, a very common example of supersaturated solutions is when they make rock candy. So what you do is you take a pot of water, you pour a certain amount of sugar in it. As you heat the temperature, the sugar dissolves. Then you put a string in the water of the sugar solution, and as you cool it down, remember, as you cool down, it usually decreases the solubility. So as you cool down the sugar solution, once you get to the temperature that forms a supersaturated solution, the sugar will crystallize on the string or stick, and that's how you get rock candy. So again, if we're using the example of ascorbic acid, if we put less than 40 grams of ascorbic acid in 100 milliliters of water, it's called unsaturated solution. If we put just 40 grams in 100 milliliters of water, it's called a saturated solution. If we put more than 40, say we put 50, then it becomes a supersaturated solution, and it will crash out. So what are some factors that affect solubility? Well, these include just two things. Temperature affects solubility, and it's always stated with the solubility. So if you ever see solubility listed, it's going to generally give the temperature. Now, most solids become more soluble at higher temperature. And if you're interested in knowing why, stay tuned for General Chemistry 2 and you'll learn why. Gases, though, become less soluble as temperature increases. And this is a funny story here. Back in the day when I was in grad school, I was traveling with my pet fish in the middle of, I think it was July or August in Georgia, where it was really hot and I didn't have any air conditioner. And what happened is my fish, probably because it was hot, but it got so hot in the car that the amount of oxygen in the water decreased that the fish ended up not making it the whole way, in addition to it being very hot in the car. So gases become less soluble as temperature increases. Solids become more soluble at higher temperature. Now, pressure only affects the solubility of gases. So for example, so if you increase the pressure, you get gases are more soluble. So a good example of this is when you take a can of Coke, it's pressurized, it keeps the carbonation in the solution. Now when you pop the top, you've released that pressure of CO2 in it, so then it's going to cause the gas to be released, therefore making your drink taste flat. Now, calculating solubility. So usually it's determined for 100 milliliters of solution is the amount of solute needed for a saturated solution. So here we have sodium nitrate. We know its solubility is 86 grams per 100 milliliters. And this is at 20 degrees Celsius, for example. What's the solubility of sodium nitrate for 175 milliliter solution? So first thing we do is we set it up as a ratio. So 86 over 100 equals X over 175. And when you solve for X, that'll tell you the amount of sodium nitrate, the solubility of sodium nitrate, in 175 milliliters of solution. So since 100 milliliters has 86 grams of solute, 175 will be more than 86. And so when we solve for X, we see it has 151 grams can be dissolved in 175 milliliters of solution. So the solubility is of 151 grams in 175 milliliters of solution. Because when you divide 151 by 75, it's going to be the same as dividing 86 by 100. Another example is, again, we're using the solubility of sodium nitrate, 86 grams per 100 milliliters at 20 degrees Celsius. What volume of solution would form a saturated solution of 35 grams of sodium nitrate? So you want to know what's the amount of solution needed to form a saturated solution with 35 grams of sodium nitrate. So we set it up as a ratio. Here we're solving for the denominator. We rearrange it to solve for X. And we see that we need 41 milliliters of solution is required to form a saturated solution involving 35 grams of sodium nitrate. And so this is how you can use Solubility is to determine the solubility in other amounts of solution or for other amounts of the solute of the same compound. Now this graph is important because this shows you the relationship between solubility and temperature. And for the lab lecture quiz, you may be referring to this to determine, to answer some questions. So let's look at one in particular. We'll look at calcium or potassium nitrate here. So we have this green curve. So below the green curve is an unsaturated solution of potassium nitrate. So if you're below this green curve at any time between 0 and 100 degrees Celsius, you're going to form a unsaturated solution. So for example, at 25 degrees Celsius, which is right about here, if we tried to dissolve, 25 grams or 20 grams of potassium nitrate, it will dissolve because it's in the unsaturated solution region for potassium nitrate. Now on the line, when you're on the line, this is a saturated solution of potassium nitrate. So for example, at 50 degrees Celsius, if I was to draw a straight line at 50 degrees Celsius, and then from there, draw another straight line, I would see that at 50 degrees Celsius, approximately 88 grams per 100 milliliters is the solubility. So as long as I'm below 88 grams at 50 degrees Celsius, potassium nitrate will dissolve in the 100 mils of water. That's an unsaturated solution. At 88 grams, for example, that's going to be a saturated solution. And then above 88 grams is going to be a supersaturated solution at 50 degrees Celsius. Now, if you're on the left side of the curve for potassium nitrate, this would be the region of supersaturated potassium nitrate solution. So again, if you're beyond, so we use our 50 degrees example, if we're at 50 degrees Celsius, if we're at, say, 98 grams of KNO3 in 100 mils, this would form a supersaturated solution, whereas this is a saturated solution, and less than 88 would be a unsaturated. So that's how you interpret the solubility curves. Now, so solubility again refers to the amount of solute needed to prepare a saturated solution. If the solute is less than the amount of solute stated for the solubility, it's an unsaturated solution. If it's greater, it's a supersaturated solution. And so here we have 238 grams of sodium nitrate and dissolved in 250 milliliters of solution at 20 degrees Celsius. What type of solution would exist? So if we go back to our previous slide, at 20 degrees Celsius, if we were to draw a straight line for potassium nitrate, and then draw a line from there to kind of approximate, you see that the saturated solution for potassium nitrate is approximately, I would say roughly 32 to 35 milliliters, grams of solute. So again, we approximated that the saturated solution is 32 to 35 grams of solute. So you get that from the graph. So we want to know what type of solution, if we put 238 grams of sodium nitrate in 250 milliliters of solution, what type of solution would exist? And here, oh, sodium nitrate, my bad. I did the wrong one. I did potassium nitrate. Let me go back. Potassium, sodium nitrate. And so if we do sodium nitrate, I did the wrong compound. We draw a straight line at 20, go over. You know, it's approximately 86 grams of solute in 100 milliliters of water for sodium nitrate at 20 degrees Celsius. And that's where that 86 came from on the next slide. So we know that based on the graph, 86 grams of sodium nitrate will dissolve in 100 milliliters of solution at 20 degrees Celsius. So we want to know what type of solution will 238 grams of sodium nitrate in 250 milliliters of solution. So first we determine the ratio between the solute and solvent and solute and solution of our solution. So 238 divided by 250 is 0.952. And then we find the ratio of solute to solution for our solubility, which is 86 per 100. And so you see here it's 0.86. So since 0.952 is greater than 0.86, this would result in a supersaturated solution. Now if we do the same thing for our other solution, say we want to make 186 grams of sodium nitrate and 325 milliliters of solution, what type of solution will exist? So again, we determine the ratio between the solute and the solution. We get 0.572. So since we know that the ratio of the solute to solution for the solubility is 0.86, since 0.57 is less than 0.86, this would result in an unsaturated solution. So again, A, we got the solubility from the graph. We approximate it. B, what we do is we find the ratio of solute to solution and compare it to the ratio of solute and solution for the solubility of our salt. If our solution has a greater ratio than the solubilities ratio, then it's going to be supersaturated, as in example 1. If I see that the ratio is less than the solubility ratio, it's going to result in an unsaturated solution, given in example 2. So these are some calculations you can do with solubility. So what's the to-do list for this module? Make sure you read over the lab lecture notes, watch the lab lecture video, look at the practice problems we do in the video, try to pause it, work them out, and then continue the video, see if you got them right. Make sure you read over the background information in the lab manual on the Hayden McNeil side for the 3rd lab, characteristic properties of substances to determine unknown substances. Complete the lab lecture quiz on this lab, do the virtual lab on the Hayden McNeil site, and then complete the post-lab assignments for this lab, which is done on Blackboard. So that's all for today. I hope you enjoyed the video. If you liked the video or learned something new, make sure to hit the like button. And until next time, this is Dr. Armand signing off.